Hello everyone. So, in today's lecture we will consider different thermal boundary conditions and we will try to find the mean temperature variation as well as for different boundary conditions we will find either the variation of heat flux or variation of temperature on the walls. First we will consider channels with uniform heat flux. So, you can see, so we have a channel where on the channel we have uniform wall heat flux boundary condition. So, Q double prime W we have given. Now, we consider that a section where x is measured from here where x equal to 0 and up to x equal to L. So, this is the length. So, obviously, you can see at this section if you consider the temperature mean temperature. So, there will be inlet mean temperature will be TMI and at any section x you can find what is the mean temperature Tm. So, as we considered here uniform wall heat flux, then your temperature at the wall Tw will also vary in axial direction. So, Tw will be function of x. So, here you can see as heat is added on the surface. So, the fluid flowing in the channel it will take the heat from the wall. So, here we wish to determine first thing is that total heat transfer rate Qs between x equal to 0 and location x along the channel. Then we want to find the mean temperature variation. This mean temperature is also known as bulk mean temperature. Mean temperature variation. So, which will be function of x, and also in this case we will see the wall temperature variation. Tw which will be function of x. In this particular thermal condition, as heat flux is uniform, then we can calculate the total heat transfer rate from the wall to the fluid. So, the total heat transfer rate Qw will be just whatever heat flux you have given Q double prime W into the surface area heat transfer area Qs. So, Q double prime W into heat transfer area As. So, what is the As in this case? So, if P is the perimeter and x is the length, then your heat transfer area As will be P into x where P is the perimeter. So, now from the energy balance we will find what is the mean temperature variation. So, we are assuming that it is a steady state, assume steady state, okay. No energy generation, negligible changes in kinetic and potential energy, no axial heat conduction, no axial heat conduction and no viscous dissipation. Okay. So, you can see that now with these assumptions, if you do the energy balance, whatever heat is transferred from the wall to the fluid, actually fluid gain the temperature from inlet while going from inlet to the distance x. So, energy added at the wall will be energy absorbed by the fluid. So, this is just simple energy balance. So, now what is energy added at the wall? That is nothing but q w, and that is q double prime w into area. So, area is P into x, okay, where P is the perimeter. And what is the energy absorbed by the fluid? So, at any section x, the m dot Cp into the temperature difference, right. So, that you can write as Tmx minus Tmi, because this is the temperature difference, and where m dot is the mass flow rate, and that you can see that it is rho into um into the flow area, okay, F. Okay. So, flow area, so that will be for pipe, it is pi r naught squared. So, this will be flow area F, and now you can write Tmx is Tmi plus q double prime s P by m dot Cp into x. So, you can see that this is the expression for bulk mean temperature variation along the x, where Tmi is the mean temperature at the inlet, and Qs, or you can write Qw here, Qw double prime, which is your heat flux constant, P is the perimeter, that is also constant for constant cross sectional channel, m dot is the mass flow rate, and Cp is the specific heat, and with x obviously it will vary. So, but you can see that m dot, so you can see that q double prime w p into m dot Cp. So, this is your constant for this particular case, okay, for constant cross sectional area duct. So, now you can see the temperature is varying from inlet Tmi to the any distance x Tm. So, the fluid properties you need to determine at the average temperature. If it is Tmi and Tm at any location x, then at average temperature you determine the fluid properties while calculating the variation of this Tmx. Now, we want to calculate the axial variation of wall temperature. So, for that we will use the Newton's law of cooling. So, from Newton's law of cooling, what you can write? So, Newton's law of cooling, what you can write? So, q double prime w, what is your heat flux at the wall, that you can write as heat transfer coefficient H, which may be function of x, into the temperature difference. So, that is your Tw, which is function of x, minus the mean temperature Tmx. In this case, when we consider the internal flows, you can see that you cannot take as T infinity or T inlet as your reference temperature while calculating the heat transfer coefficient or the Nusselt number. Here we will consider the bulk mean temperature at any cross section. So, while writing the Newton's law of cooling, the wall heat flux we have written as the temperature difference as T w minus the mean temperature T m. So, for internal flows we will consider T w minus T m. So, you can write the T wall which is your function of x, you can write as T m x plus q double prime w divided by h x, and T m x already we know, okay. T m x we have written as T m I plus q double prime w p x by m dot c p. So, you can write in terms of T m I now this T w x. So, if you substitute this, you can write T m I plus q double prime w p x divided by m dot c p plus q double prime w by h x. Okay. So, you can rewrite it as T w x is your equal to T m I plus q double prime w, you can take it outside. So, you can write p into x divided by m dot c p plus 1 by h x. Now, you can see that to calculate the wall temperature variation you need to know the heat transfer coefficient, because H is your heat transfer coefficient. So, you can see from this expression T m I is your inlet mean temperature, that will be known, this is your wall heat flux, that will be known and it is constant, P is the perimeter, x is the axial direction. So, at any location x you can calculate the T w, m dot and C p are also known, only unknown is h x. So, you can see that while deriving these we did not take the assumption whether it is laminar or turbulent or the region is developing or fully developed. So, this expression, this T m x and T w x is the expression of T w x and T m x are valid for both laminar and turbulent flows as well as for entrance region as well as fully developed region. Only thing is that while calculating the wall temperature you need to calculate the H x, and H x will depend whether it is developing region or fully developed region, at the same time whether it is laminar or turbulent flows. So, this H x we need to find. Okay. So, depending on H x, if you know H x, then you can find T w x for constant wall heat flux boundary condition. Now, let us consider channels with uniform wall temperature. So, you can see this is the channel at x equal to 0, you have inlet mean temperature T m I, the walls are maintained at temperature T w and T w is constant. So, in this case you can see that heat flux is not constant. So, heat flux will vary in axial direction. So, for that reason while solving this problem we cannot consider the full length of the channel as we considered for the uniform heat flux case, because in earlier case the heat transfer rate Q w you could calculate using q double prime w into the surface area A s, but here as q double prime w is not constant for uniform wall temperature condition. So, obviously we cannot consider the full length and do the energy balance. For that we will consider a small elemental area in the flow region and we will do the energy balance. In this particular case also our objective is to find what is the axial variation of mean temperature, axial variation of the heat flux and what is the total heat transfer rate at the wall. So, we wish to determine the following. One is total heat transfer rate, Q W, then mean temperature variation, mean temperature variation. Okay, so, T m as function of x, and in this particular case as T w is constant. So, we want to calculate the wall heat flux variation. Okay, Q double prime w as function of x. So, now in this region you consider one small elemental volume, okay, at a distance x of distance dx. Okay. So, at this inlet of this elemental volume you can see that we have the inlet mean temperature as T m. Obviously, at a distance dx using the Taylor series expansion, what you can write T m plus dt m by dx into dx. Okay. So, at a distance dx using the Taylor series expansion you can write this, and so you have the wall temperature constant. So, there will be the heat transfer from the wall to the fluid in this elemental volume. So, that is your dQW. So, whatever heat is added here, the fluid which is passing through this dx distance, that is actually that fluid absorbed this heat. So, you can do the energy balance as, so applying conservation of energy to the element, what you can write dQ W. Okay. So, dQ W is the heat added to the fluid from the surface. So, what is the heat absorbed, that is your just m dot Cp into delta T. Okay. So, delta T is nothing but, you can see it will be T m plus dt m by dx into dx minus T m. So, this is the temperature difference. Okay. So, you can write dQ W is equal to m dot Cp, m dot is your mass flow rate, Cp is the specific heat. So, this will be just dt m. Now, you apply the Newton's law of cooling. So, Newton's law of cooling, you can write dQW. Okay. So, that you can write the H which is function of x, that temperature T wall minus T mx, okay, into the area. So, area is P into dx. Okay. So, this is the P is the perimeter and dx is the length. So, your heat transfer area will be P into dx. Okay. So, now this both you can equate. So, if it is equation number 1 and if it is equation number 2. So, from equation 1 and equation 2 you can write m dot Cp dt m is equal to H which is function of x T w minus T m into P into dx. Okay. So, now you rearrange it. So, dt m divided by T w minus T m is equal to P H divided by m dot Cp into dx. So, now you integrate it from x equal to 0 to any distance x. So, if you do that, so now integrate this. So, from at x equal to 0 you have T m I, and at any distance x you have T m dt m by T w minus T m is equal to, so you are integrating 0 to x p h, which is function of x by m dot C p into dx. So, now you can integrate and put the limits. So, this you can see it will be ln, so it will be T m x minus T w, just I have changed T m minus T w and T m I minus T w. So, as I have changed this, so there will be a minus sign. So, you can write minus, and you see p m dot and C p are constant. So, you can take outside the integral. So, you can write 0 to x h x dx. So, if you know the variation of heat transfer coefficient in axial direction, then you will be able to integrate this. So, we can find the average heat transfer coefficient as average heat transfer coefficient okay. So, that will be your h bar, you can write as 1 by x 0 to x h x dx. Okay. So, now we will substitute this part as x into h bar. So, if you do so, you can write ln T m x minus T w divided by T m I minus T w is equal to minus P h bar, which is your average heat transfer coefficient, divided by m dot C p into x, this x. So, h bar into x. So, you can now find the axial variation of mean temperature as T m x is equal to T w plus T m I minus T w into e to the power minus P h bar by m dot C p into x. So, you can see your mean temperature varies exponentially, right. So, you can see that while deriving this expression, we did not assume whether flow is laminar or turbulent, or whether it is entrance region or fully developed region. So, this is valid for all the conditions, but now you have to find what is the heat transfer coefficient. So, while finding the heat transfer coefficient, you need to have these assumptions whether it is laminar or turbulent, or it is entrance region or fully developed region. So, now let us calculate the total heat transfer rate from the wall. So, we can write total heat transfer rate So, total heat transfer rate Q s or sorry Q w. So, what is that? We can write m dot C p into T m x minus T m I. So, you can write and Q double prime w, which is your heat flux. So, that also we have found as h function of x T w minus T m x. So, you can see that once you calculate the h x, so T w is known. So, you can calculate the mean temperature. Once you know the mean temperature, then you can calculate the total heat transfer rate as well as the heat flux. So, this is your wall heat flux. So, because Hx you need to find. Okay. Once Hx is known and Tmx is known from this expression, then you will be able to calculate what is the wall heat flux Q double prime W. So, now for both the thermal conditions we have found what is the axial variation of mean temperature as well as the total heat transfer rate. Now, let us see the variation of this bulk mean temperature of the fluid in the tube. So, you can see for uniform wall heat flux. So, what is the variation of Tm? Tm, which is function of x, we have written as Tmi plus Q double prime W P by m dot Cp into x. So, how it is varying? You can see your Tm is varying linearly, because Q double prime W P by m dot Cp, this quantity is constant. So, Tm is varying linearly with x. When we consider uniform wall heat flux, the Tm variation we have seen Tmx is equal to Tw plus Tmi minus Tw into e to the power minus P h bar divided by m dot Cp into x. So, in this case you can see your mean temperature varies exponentially. Okay. So, now if we plot, so this is your temperature axis and this is your axial direction, and in this case also this is your temperature axis and this is your axial direction. Okay. So, your this is your x, okay, and this is your t. So, now you can see that in this case you have uniform wall heat flux, right. So, uniform wall heat flux. So, you can see that also we have found. So, here you can see that T W x minus T m x is Q double prime s divided by h, which is function of x. So, now you can see that in this particular case H x is unknown. Okay. Obviously, your heat transfer coefficient will vary in axial direction, but we will show later that in fully developed region, fully developed means both hydrodynamically and thermally, in that region H is not function of x, H is constant. Okay. So, if you plot H, okay, with axial direction, then you will see that when the fluid is entering in the channel, so it will have very high heat transfer coefficient. In the developing region it will gradually decrease, then once it will become fully developed both hydrodynamically and thermally, then your heat transfer coefficient will become constant, and we will show it later that H is constant for a fully developed flow. So, if we plot this H as a function of x, so in the developing region it will decrease, then after that it will become constant. So, you can see if this is your entrance region or developing region, then it will gradually decrease, and in fully developed region you can see H is no longer function of x, it is constant. So, in fully developed range H is constant, okay, and in this region H is function of x. So, you can see that T w minus T m, which is q double prime s by, so you write w, sorry, q double prime w by h x. So, in fully developed region h x is constant, hence T w minus T m will be constant. Okay. So, in fully developed region T w minus T m for uniform wall heat flux boundary condition will become constant. Okay. This is also true that fully developed region H is constant, okay, for uniform wall temperature. So, H is constant for both the thermal condition, uniform wall temperature and uniform wall heat flux for both hydrodynamically and thermally fully developed region. So, now you can see here uniform wall heat flux. So, your T m will vary linearly, okay. You can see from this expression. So, you draw this. So, this is linear variation, okay. So, this is your T m, which is function of x, it is varying linearly, and you can see that T w minus T m will be constant in a fully developed region. So, if you see that this is your fully developed region, okay, and this is your entrance region, then in this region, fully developed region, T w minus T m will be constant. So, you can see that your T w also will vary linearly, okay. So, it will also vary linearly. So, this is your T w x, and you can see that this difference in fully developed region it is constant, T w minus T m is constant, okay. However, in your entrance region, okay, there will be variation. So, it may vary like this, okay, and this is your the temperature difference T w minus T m, okay, at inlet, okay. So, this is the temperature variation, okay. So, you can see that this T w will vary linearly in the fully developed region, and so that T w minus T m will remain constant. Now, you plot for uniform wall heat flux. So, for uniform wall heat flux, so T w is constant, right. So, you can draw this T w, it is constant. So, this is your T w is constant, okay, and your T m will vary exponentially. So, if you plot it, so there will be variation like this, okay. So, this is your T m which will vary exponentially with x. So, this is your delta T I, okay. At inlet the temperature difference, okay, delta T I is your T w minus T m at inlet. So, you can see that there will be always decrease in the temperature T w minus T m. T m is function of x, but T w is constant, and that you can see from here that it will how it will vary. So, you can see T w minus T m, okay. So, it will be T w minus T m I into e to the power minus P h bar by m dot C p into x. Okay. So, Tw minus Tm, this difference will vary like this. Okay. So, in today's lecture we considered two different types of thermal conditions. One is uniform wall heat flux and uniform wall temperature, and we have just done the energy balance and we have tried to find what is the variation of mean temperature and the total heat transfer rate from the wall in both the cases. However, in uniform wall temperature case, your heat flux at the wall also will vary. So, we have found what is the variation of wall heat flux in axial direction, and for uniform wall heat flux your wall temperature will vary axially, and we have found what is the variation of Tw with x. Then we have plotted this temperature, mean temperature and the wall temperature, and also in this expression of mean temperature we have seen that your heat transfer coefficient arises. So, depending on whether the flow is laminar or turbulent, or whether it is developing region or fully developed region, you need to find the heat transfer coefficient. And also we have told that in fully developed region, for both the thermal condition your H is constant. So, for a uniform wall heat flux condition, Tw minus Tm will be constant. However, in uniform wall temperature boundary condition, Tw minus Tm will also vary exponentially. We have plotted this mean temperature and wall temperature for both the thermal conditions, and we have shown that in fully developed region the temperature difference between wall and the bulk mean temperature will remain constant as your heat transfer coefficient remains constant in fully developed region for both the thermal conditions. Thank you.